from ASAP. And today we have a session for 6th semester civil engineering students. And the subject is computer programming and computational technologies. Session is Lagrange Interpolation method from Module 5. And to deliver the session, we have here Dr. Praveen from Rajiv Gandhi Institute of Technology, Kottayam. And about him, he started his teaching career in the year 2000, prior to which he was associated with the industrial sector involved with environmental and bioenergy technologies. His key research interests are in the domain of sustainability and built environment, energy efficient wastewater treatment processes, and impact of climate change on infrastructure. Adding to that, he could also generate IP products as outcome of research activity. He was awarded PhD by National Institute of Technology, Calicut, and his master's and bachelor's being from University of Kerala and Calicut, respectively. With great honor, I, on behalf of ASAP, welcome you to the session, sir. And I welcome all the attendees out there to the session. And before we start the session, attendees, please note that you can use the Q&A option available on the screen to post your doubts. And your doubts will be cleared by the professor in between the session. Thank you all. And let's move on to the session. And over to you, sir.
Okay. Thank you very much, Rajiv. So we move to the second part of our lecture that's on this module. This, as it is already stated, is on Lagrange interpolation method. The word interpolation is a very important process in your data analysis. This, any point to define this particular term, interpolation, it would mean that in any data analysis, you would be required to estimate data which has not been made available to you. That means from the two given data sets, when you are required to estimate a data which is not provided, you should be available, or you should be in possession, or you should have an appropriate tool to identify or to estimate that using value. So this lecture is precisely to understand what are the various ways in which we should be able to come out with such techniques. Okay. Now, yes, no, yes. So if you look at this graph, this is a quick illustration of what we are trying to do today. You see a graph in which data points are already plotted. So they are the known values which are always available to you. Let us say you are civil engineering students, so obviously we all have done experiments on simple tensile test on a steel bar. You will have stress values plotted along X, and might be you will have a strain along the other axis. But in case if I ask you the stress value, it is not recorded on your plot, or maybe a strain value not recorded in a plot, then from the known information you should be able to estimate this missing value. This is what is given as arrows. Arrows that have been represented are the spaces where we need to find these values. This is where what we normally call interpolation. As you see, from the small node that is already written, to find a value between two given data points from out of something that is already given to you, that find something that is not available. Now let us move to the other part. You see some space which is beyond the floated blue dots. Still, you might have to get some values there too. We call that process of extrapolation. That's again a different branch of data analysis, which we will not be looking at this today. Of course, that's a forecasting and all those things detailed analysis. Now what we try to do is we look at how can we get something missing between these plots that are available. Okay, a brief overview of the process. With this, we move to the next part of the specific method for our data analysis. That's Lagrange Interpolation method. Let's say you are given a set of data points. Let us look at it like this. You are given data points. See here, x1, y1. It's a set. You have an x-axis. Correspondingly, you have another y-value. Another data set, x2, y2. You have third data set, x3, y3. And it goes on. You have an x, n, y, n. So you have n paired sets which are there, which is plotted. And we need to evolve something between is asked. How can you get this value? That's what the whole idea is. So the broad philosophy, what you must have in your mind when we move to the next part of this session is we are trying to get a characteristic function which will accommodate all the data that's given. That's the first aspect. That means we have a common function which will include all the data. And perhaps that function will enable you to get something missing. As simple as that. So our issue is how can you go forward to get such a general function which can accommodate all the data that have already been made available to us. So here we have even it goes until x minus xn, as you see here, x minus xn, plus a1 into this way it proceeds till again n. You have a2. Likewise, it goes and you have an multiplied by this. Now, one process we are trying to establish a general polynomial. When I talk about general polynomial, again, I would call you, all of you, to have in your mind. You have, on one hand, you have a data set that every x you have a y value. On the other hand, you are trying to have a polynomial. What does that mean? If you drop your x value into that polynomial should be able to give you a y value. Likewise, for all data sets, your polynomial should satisfy the given data. With this in mind, you must also understand, maybe if you take yourself long back, if I say x equals a is, or x equals a satisfies this function, fx equal to 0 is a function, x equal to small a, I'm just giving an illustration to you, nothing to search from the slides. So if a equal to 0 is a function, that means x minus a is a factor of your polynomial. I suppose you remember long back when you based this. X minus a is a factor. Likewise, here I have x1, x2, x3, likewise xn. Everything should be a factor here. That's why in the process that we have adopted to identify a polynomial, we have written is that a naught x minus x1 into x minus x2. Likewise, you are given such an elaborate polynomial here. Now, our objective is not here. We are just starting up to identify which should be the right polynomial. This is a general stage that we are written, in which a naught, a1, a2, likewise it goes. I have stated it to be a coefficient. That's all. We have to find out what these values are. Now we move to the next to get what would be the coefficient of this. So when you go to the coefficients, So you look at the coefficients. Now you see, this is the same function I written here at the top for the easiness of understanding. Same thing which you written on the previous slide. Now, if you look at this, our objective is, we have x0, x1 till xn. If I substitute x equal to x0, let's look at this value alone, x equal to x0, into this function, the fx equals a naught series of these terms until an series of this term. If I substitute x equal to x0 into this, you see here there is no x0 on the right coming. Look at this a1 into x minus x0. The moment I drop x0 for x, this entire thing will vanish. If I drop x0 here, entire thing will vanish. If I drop x0 here, entire thing will vanish. If I drop x0 here, entire thing will vanish. So you can say that if I drop x0 into this whole function, my f of x0 is definitely y0. Y0 will be equal to x0 coming for x minus x1, x0 minus x2. Likewise, it goes. So on the first coefficient series will remain in this function. You get this. This will be the first thing which I get. Likewise, if I substitute x equals x1, you can see this will vanish, but this will remain. This will vanish, this will vanish, this will vanish. So entire thing other than a1 will remain. So I will have another equation. When I substitute x equal to x1 as y1 equals a1 into x1 minus x0, x1 minus x2, x1 minus x2, and it goes like that. Now again, if I substitute x equal to x2, you can see the first term, a0 terms, this entire first line will vanish. This also will vanish because x minus x2, I'm substituting for x equal to x2. This also will go off. Whereas here, you don't see x2 constant in anywhere. So your x can take x2 and it will remain there. Whereas you can look at this, the x2 here will vanish. So this also will go. So when I substitute x equals to x2, I have only y2 equals a0 into this. Sorry, this is wrong. This is a2 comes. Y2 into a2 into this one. Likewise, when you substitute each of this, I get a function like this. This will be a0, this will be a1, this will be a2, this will be an, likewise. So you get, this is the series, this is the equation that we get, from which I need to calculate what is the value of this coefficient. Okay. By this time, these are all constant because x0 is your data point, x1 is your data point, x0 is a data point, x2 is your data point. When you deduct this, you get a constant term. So when you multiply all this, a constant term. A0 is your value is equal to y0, for which you can calculate A0. That's what we see in the next slide. Yeah. So this is what I got in the previous y0, y1, y2, y3. I can write like this. The same thing. A0 equals y0 divided by this entire thing. I suppose you understand. A0 equals y0 divided by this entire thing. A1 of this line equals y1 divided by this entire thing. Yeah, x minus x0, x1 minus x2, x1 minus x3, likewise this. So this entire terms goes as a denominator to y1 to give you the value of a1. Likewise, it goes an. This is an. So an equals yn divided by this entire term. You see how you get the coefficient. Now you got this coefficient. Now this coefficient should go back to your initial polynomial. So this was your polynomial. This was your, so this is the coefficient. If you look at this previous, this is the coefficient which you have got to the previous slide. This is the same thing that written here for easiness of discussion. But this you are applying to this equation. This is the equation which we have considered at the start. So you want a general polynomial equation, get the Lagrange function. So this is for a0, a1, a2 until an. You have got all the coefficients through these operations. Our job is to substitute for these coefficients, the values that we have got here. So this will go, this entire set of results for A0 to AN will go into this general function which is shown below. So we get like this. Why not? Of course, we look at this. Why not is A naught is Y naught by this. This will go into this A naught will capture this value. Now if you look at this value, this is your both terms. Y naught divided by the entire term is here, and already these terms in function here, your function here has these values. So A naught will be Y naught divided by x minus x1 and the related terms. These long terms on the numerator and denominator I am representing as N naught. So if you look at the slide, it's very easy. So now you see, so this is the general function you get at the Lagrange polynomial or Lagrange interpolation. So if you got n sets of data, we've got x naught, y naught, x1, y1, x2, y2, like x and y1. You can use this general function. It's very simple. You observe very closely. If you observe very closely, you can see that x minus x, this is your first data set, zeroth value is x minus x1 goes to serial mode, x minus x2, x minus x3 goes to x minus n. And the denominator comes the first value, x naught. Likewise, it goes x naught finds same thing, x naught finds x1. X naught finds. So top is a variable x. On the denominator, it is the x value, data value corresponding to this equation. This is what's called as an interpolation equation. This is what's called an interpolation equation. N values are interpolation. N0 is first interpolation, N1 is the next interpolation, Nn is the next interpolation. Details will become clear as we move forward to the short problems. So now what we are given here is in general. It looks very big for you. It's very simple. When we move to the very specific analysis steps of various problems related to short problems, then you just tailor this problems down, or maybe this entire equation, which is shown on the screen, is to be reduced or is to be minimized to the specific requirement of certain problems. This is what we are trying to illustrate in the following slides. Now let me take just 2 data points. Now what we have taken earlier, we have generated a function with n data sets, n, that means x1, y1, x2, y2, till xn, yn. Now what we are trying to do is we take just 2 values, x1, x0, y0, and x1, y1. As is shown here, x0, y0, and x1, y1. To take these 2 values, how can you use this Lagrange interpolation function, get value in between? That's the first question. So if you, I just have to glance to this equation again. Look at n. See, for n data sets, you have x minus x1, x minus x2, likewise it goes. So you're talking only one data, that means you take only first term, one data, this one. And for one, you have got 2 data sets. For 2 data sets, you just need 2 interpolation functions. As you see here, you'll have n0 x0 plus n1 xn. Okay. To make it more easier, I can tell you, if there are n data sets, n data sets, that means you start from 0, 1, 2, likewise it goes to n. How many terms do they use? They use n plus 1 terms, because it starts from 0, 0, 1, 2, 3, likewise it goes to n. So number of terms that you use here is n plus 1. So when you have 2 data, so when you have just, that is there are 2 times for you have n terms, you got, if you got n data points, you got n plus 1 terms. This is something which you should keep in mind. So now you see you got 2 data points here. Now you got n0 x0 and n1 x1. This is it. From the interpolation function, your n0, what you got is x minus x1 and x0 minus x1. N1 is x minus x0 and x1 minus x1. Look at this one. X minus x1 and x0 minus x1. The first term. N1 is x minus x0 and x1 minus x1. This is one first term for the interpolating data sets. This is what we call as linear interpolation function. So two data points are given. We are using this. Please make it more clear as we take the problem. And this basic understanding is necessary for you to get a feel of what is interpolation. Now, if you look at three data sets, what's called quadratic interpolation. At least from your course perspective, you should try to operate upon a linear interpolation as well as a quadratic interpolation function. When you have x naught, y naught, and you have x1, y1, x2, y2, you have got three terms coming in. X naught, x0, because you are trying to build up a function, a generic function comprising all the three. That's what we try to do. We are having generic function comprising all the three. So any value in between this general function should be able to give us. In the previous case, you are having a generic function comprising, to get any value between these two, using a function like this, n0 x1, n1 x1. Whereas for n values, you have n such terms, n plus such terms available. That's what you must have in mind. So you are trying to draw generic function. If you look at this 2 points, when you connect this straight line, you see here the variable that you have, x is this, take the single degree. That's this straight line, ax plus b, the straight line. Now, whereas here you see we have got three terms, there are three interpolated functions. So, if you have a quadratic response that we'll see next. So, look at this. You got n naught, x0, n1, n2, x2. This is a quadratic. Linear, you had only two. When it comes to quadratic, you had three, because again, two terms comes into the picture. Okay. So two terms coming in this picture. So, if you look at the earlier case, it was only linear, it was only one term, x minus x1, x naught minus x. Now, you go to the first interpolated function, will have x minus x2 also included, x naught minus x2 also included. Next interpolation, n1, x minus x naught, 1 doesn't come here, you go to the x minus x2. Denominator, we have x1 coming here, x1 minus x naught, x1 minus x2. Similarly, you have n2, you have this value coming here. You have x naught and x1 occupying the numerator, x2 with the value which goes to the 1. So this is how a generic interpolation function for Lagrange interpolation function will help you. Now when you multiply this, you get x squared terms comes out. So that means it's quadratic in nature. So you get a quadratic polynomial and a generic polynomial to give you what is the generic characteristic. The data points already taken. So you have general function, you got a out of the general function, we are trying to form how can you get a linear polynomial and also how can you form a quadratic polynomial. Now let us say how we can use a problem. This will give you a better input to you. Look at this. Look at this. This is a practice problem. Okay. Now if you look at this, this is an interpolation question is given there. Interpolate corresponding to x equal to 4. That means you're given a data set here. You try to see x equals 2, 3, 5, 8, 12. Corresponding values of fx is given as corresponding to x equal to 2, you have fx value 10. Corresponding to x equal to 3, you got fx value 15. Corresponding to x equal to 5, you got fx value 25. Corresponding to x value 8, you have fx value 40, 40, 12, and 16. You have to get what x equal to 4. A value somewhere here. Okay. Something that comes into your mind is, can I use only these two data sets? That means 4 comes between 3 and 5. So I can get an interpolation between 3, 5, and 10. That. Let us take that next. You can have, now what we try to do is, how can you make a general polynomial comprising the entire data? So that polynomial will help us to get any missing data which is not reported by this tabulated. You want something between 2 and 3, or something between 3 and 5, or something between 5 and 8, or something between 8 and 12. That polynomial should be able to give you what's the corresponding f of x value. So here we use the general polynomial function which we have derived or which we have formulated before. Let us say, for this entire data sets, I'm suggesting the polynomial f of x equals n0 y0, n1 y1, n2 y2, n3 y2, and n4 y2. Okay, so you have got one, two, five terms coming in to connect between. You have got polynomial interpolation functions connecting all the five terms, n0 y0 plus n1 y1. Now, if you look at, so you take the first four terms that are required here. You got four polynomials, so five polynomial functions. 1, 2, 3, 4, 5. So your n0, same. See, this was, your linear function had x minus x1 by x0 minus x1. Your quadratic had x minus x1 into x minus x2. If it had been cubic, you would have go for x minus x3. Now you don't have to look at the degree. We just need so much terms. So how five terms or five data points are there? So we have to choose the five polynomials to interpolate across these five data points. That's all. So we need five-term polynomial. Five interpolated functions need to be added to get our generic polynomial. So you look at the numerator. Our first term is represented as x minus x1 and x minus x2, x minus x3, and x minus x4. Denominator comes as x naught minus x1, x naught minus x2, x naught minus x3, x naught minus x4. You can just try to observe closely. You should be able to get an idea on how that Lagrange interpolation process involved. Now, if you come to n1, the second polynomial, you can easily see, x minus x naught comes to the top, x1 cannot be there, x minus x2, x minus x3, x minus x4. Denominator comes again. Instead of x, it will be x1 minus x naught, same time, x1 minus x2, x1 minus x3, x1 minus x4. If you look at n2, another set of third polynomial. But x minus x0 here, same as this, but n2 doesn't come here, x2 doesn't come here. You got x minus x3, you got x minus x4. So in the denominator, you can see x2 comes here. So you have same x2 instead of x2 minus x0, x2 minus x1, x2 minus x3, and x2 minus x4. Look at n3, same relationship, the same approach exists here too. X minus x naught, x minus x1, x minus x2. You don't see x minus x3. Get x minus x4. x3 comes with the denominator. x3 minus x0, x3 minus x1, x3 minus x2, minus x4. Same as the fifth polynomial, n4. Look at this. Last term is not there. X minus x4 is not there. You got every continuous term still x minus x3. And denominator is for x, you get x4 minus x0, x4 minus x1, x4 minus x2, x4 minus x. So we have got a polynomial set to give a general Lagrange interpolation equation for this entire data set. Now we will move ahead. How can we operate this upon? I'll just play the data set again for the easiness of our discussion. Let us say, if you remember here, these are our data. Now you have x naught. Look at this again. I will explain again. X naught is what? X naught is 2. X naught is 2 here. First value, x naught is 2. What is x1? X1 is 3. So this is likely 2 minus 3. That's what? 2 minus 3. Look at this. X naught minus x2. This is 2 is x naught. What is x2? X2 is 5. So look at 2 minus 5. So numerator again remains as x minus x3, x minus. So that means numerator you can have x minus x1, x minus x1 is x minus 3, x minus x2 is x minus 5. So likewise, you can try to look at x minus x1. 3. X minus x2 is 5. X minus x3 is 8. X minus x4 is 12. Now you have x naught minus x1, x naught minus x2, x naught minus x8, x3, x naught minus x12. Okay, so your function is n0, y0. This entire numerator and denominator together, you get this as n0 multiplied by your y0 value. What's the y0 value? x0 and y0. Y0 is 10. So when you have y0 here, so here they multiplied, you get a function of x as the first term. Now, if you come to the second term, n1, y1, x0 minus x0, 2. You don't have x0 minus x1. You go for x0 minus x2 because n1 term, x0 minus x2. Here, x0 minus x3, 8. Sorry, x minus x3. You have x minus 12 coming in. So you have the numerator. Now, corresponding, this numerator, you have what is the corresponding denominator you have? You have all values deducted from x1. So x1 is 3. So 3 minus 2, 3 minus 5, 3 minus 8, 3 minus 12, multiplied by y1. What equals y1? Y1 is 15. You can look at n2, y2. You got x minus x2 again, x minus x3, again, n2. This doesn't come. You go to n x minus x. You have x minus x3, and you have x minus x4. And you go to corresponding x0 value, x minus x2 divided, this and the numerator divided by x3 minus x0, x3 minus x0, x3 minus x1, sorry, x2 minus x1, this is x2 minus x0, x2 minus x1, x2 minus x3, this is x3, this is x4. So you have x2 minus x4. 25. This is the value y is 25. Same n3 values x minus x0, x minus x1, x minus x2, x minus x3 is not there, x minus x4. Corresponding x3 minus x1, x3 is 8, x3 minus x1, x3 minus x2, x3 minus x0, x3 minus x1, x3 minus x2, x3 minus x4 into 40, y0, sorry, y3, y3. Now coming back n4 into y4, you got x minus x2, x minus x0, x minus x1, x minus x2, x minus x3, x minus x4 will come here. You have for x4 value, so x4 minus x0, x4 minus x1, x4 minus x2, x4 minus x3 multiplied by y4, that is 60. So this entire is a polynomial set. So when each of this n0, y0, n1, y1, n2, y2, n3, y3, n4, y4 get added up, you get a polynomial of some degree. There is x raised to 4 degree to get, which represents the general polynomial, which will represent this entire data. We are getting a general polynomial, which will represent all the 5 pairs of data which we have got. This is what is given by Lagrange Interpolation. Now, to get, you are asked a value, what is x equal to 4? So to get x equal to 4, you can directly substitute this value x equal to 4 into this, as shown in the next slide. So what we need to get is x equal to 4. So this is a general polynomial which have gone there. So I'm substituting x equal to 4 into this. X equal to 4, this is general. So what we need to do, this was your general polynomial. The general polynomial, you have evolved this polynomial specific to this data set. Corresponding to this, I will rewritten again for the sake of discussion. Bring everything together in your mind. This was the data set given to you. This is the general polynomial that we have evolved. This general polynomial, all these coefficient values were substituted. You got the previous slide, and this in this slide. So we are now all going to operate on this polynomial set to get what's the value of x equal to 4. So to obtain x equal to 4 and value at x equal to 4 is x4. So we get this f4. You get n0 y0 plus n1 y1 into y2 into y2 plus n for y4. This is a general polynomial. In which you have to substitute for x as 4 values. Now let's see how he does this. Look at this previous slide. You got this general equation n0 y0 plus n1 y1 into y2 y3. You substitute 4 for all x here. All x, substitute 4 values. So 4 minus 3, 4 minus 5, 4 minus 7, 4 minus 12. Here again 4, here also 4, here also 4. So substitute 4 with all the polynomials here. When you multiply with corresponding y0, these are the values that you have got here. These are the values that you get here. So these values are the terms n0 y0 with minus 1.774, n1 y1 it is 10.667, n2 y2 is 12.698, n3 y3 is minus 1.778, n for y4 is 0.91905. And stop. Think of it. Get f4 is 20. This is the answer for the f4 is 20, or based on the Lagrange Interpolation function. Thinking, evolving a polynomial, considering all the 5 data sets given. The most generic form of polynomial which can evolve. Address this. Now, I'll just try to take you to the small parts through which the same answer can be addressed to give you a wider understanding of Lagrange polynomial function. Yeah. Now let us say we have evolved. Now let us say I'm trying to apply linear interpolation to this. That means, I say, what we say is sometimes for the problem, for the exams, they might give you 2 sets of data. And you might be asked to find the data in between. So if you are asked to find the data in between 2 data sets, here also, P5, 15, 25. I'm just taking out this pair, P15 and 525. 4 lines between. So why can't I have a linear interpolation between these 2 data sets? So if I apply linear data interpolation, I can have f equals n0 y0 plus n1 y1. Linear, just need 2 terms. So my n0 y0 value is what? N0 y0 gives as x minus x1 divided by x0 by x1 multiplied by y0. So what's my x value? X value, I have skipped the one general equation step. I suppose at this time you will be able to understand that. We got 4 minus 5. What is x1 value? X1 value is 5. 4 minus 5. X value required is 4. 4 minus 5 divided by x0. 3 minus x1. 5 multiplied by y0. So that 15. Okay, 7.5. What is n1 y1? X minus x0 divided by x1 minus x0 into y1. Okay, so y0 is y1. So 4 minus 3. 4 minus 3. 4 is x. 3 is x0. So x minus x0. Previous case is x minus x0. X minus x0 divided by x1 minus x0. x1 is 5. 5 minus 2 into y1, 25. 25. So when you multiply this, you get 12.5. So when you add this n0, y0, n1, add, okay. So you can also use a linear interpolation, the same answer, just to give you the illustration of how different methods can be applied to get a solution for a given data. Now let's use the same quadratic interpolation. Let us add, what we try to do is we take only 3 sets of data. we'll take three sets of it. So if I take for quadratic, we need 3 points. So 2, 3, and 5. I'm taking this. Apply quadratic interpolation across this 2, 3, and 5. 10, 15, and 25. So we have 10, 15, and 25. And 4 will lie in between 3 and 5. So let me establish an interpolation function consisting of 3 data points. And there, I'll take a general equation to comprise this, all the 3. So that equation should be able to give me any value that lies between these 3 data points, 3 and 5. Anything which comes between, this interpolation function should be able to give. So now let us go the process according to the Lagrange interpolation. You have fx equals n0 y0 plus n1 y1, n2 y2. In quadratic, you have 3 terms. If it's linear, you have 2 terms. When you have, if you have 4 data points, you have 4 terms. When you have 5 data points, you have 5 terms. That's why this problem, earlier we took 5 terms because we have 5 data. Okay. Now, if you look at this, x minus x1. So your n0 into y0. So your n0 will be x minus x1 into x minus x2. You got x0, x1, x2. So x minus x1 into x minus x2 divided by x0 minus x1, x0 minus x2 into y0. How can you apply this here? Here also, when you look at this, x is 4 because the required value of x that you want is 4. So you're taking x as 4. 4 minus 3, x1 value, 3. X value, 4. Minus x2 value, 5. So this is x minus x1, the other is x minus x2. Divided by, you have got x0 minus x1. What is the value of x0? 2. This is minus 3. That is x0 minus x1. This is x0 minus x2. So we have 2 minus 3 and 2 minus 5. So when you operate this, you get n0 value multiplied by y0 is 10. Y0 is 10. But I 10. So into 10, you get minus 3.3. This is what the value. Now, n1 y1, when you try to do x minus x0 into x minus x2, n1, x minus x0, x minus x2. So x1 term is not there. X minus x0 is x minus x2. And for x, the denominator it comes x1 minus x0, you got x1 minus x2. Multiplied by y1, as it is there, y1. Again, substituting here 4 for x minus 2 for x0, 4 for here for x. For x0 you get 5, x1 you get 5. So you get x2 for 5. So you get x minus x0, x minus x2. x1 term is not here for the n1 polynomial. So here again, x1 minus x0. x1 is 3, 3 minus 2. The other is x1 minus x2 is 3 minus 5. You get this multiplied by 50. Get 50. Okay. Now come to the third polynomial, n2 y2. X minus x0 into x minus x1. Your third, second, x minus x2 is not there. Then the next term, denominator you have for x, you got x2, x2 minus x0, and x2 minus x1. This is 1, 2. So when you substitute for x and x0, you get 4 minus 2. 4 is x, 2 is x0. Other x minus x1, 4 is x, and 3 is x0. Denominator you have 5 minus 2. Why? Because x2 is 5 and x0 is 2. So x2 minus x0 is 5 minus 2. And x2 minus x0 is 5 minus 2. And your y2 value is 25. Multiply 25. So you get it as 8.3233. Your net polynomial value for x4 is sum of all the 3 terms. When you add all the 3 terms, you get a 20. So you get 20 as the interpolation. So, irrespective of the type of polynomial, because you are finding equations through exactly through this data points, key data points. You get the same equation. Linear also connecting these same equations. The other equation also had the same function to all the four. Some common characteristics you are able to get as the result for all. I suppose this is the general understanding of the Lagrange interpolation process, which we have chosen in this discussion. So, from the exam perspective, we should be able to understand or we should be able to explain what does, in general, Lagrange interpolation function mean, how a general polynomial structure for Lagrange interpolation can evolve as one. Now, when it comes to problems, how can you apply this Lagrange interpolation for linear interpolation process and also quadratic interpolation process? And you can evolve or you can estimate the missing value as specified. This slide should be able to give a great idea on how to operate upon the Lagrange. So with these, I think we have discussed two major components that are required as per Lagrange, as per your curriculum. Interpolation, like because I specifically told you Lagrange interpolation. You've got different techniques of interpolation. As syllabus specifically stated, Lagrange, how discussion shall be limited to Lagrange. And also, as a student of this technique, you must also understand that, as I said, when you take this data set, this is something which you should at the end have in mind. You do an experiment. Let me close with the same example which I stated here at the start. When you do a simple tension test, most probably you will have load 2 kilonewton, or maybe start from 1 kilonewton. You note the deflection, 2 kilonewton, note the deflection, 3 kilonewton, deflection, 4 kilonewton. So you have incremented your load by 1 kilonewton. Your intervals are very constant. Lagrange interpolation, so that means when you get the data, Lagrange interpolation is so flexible that your data intervals need not be same. That means if you have data, first data is 1 kilonewton, next data is 2, next is 5, next is 9, next is 13. Your interval is varying, or even it can reduce or increase. It is, you can say, they don't remain constant, can vary. Even under those conditions, Lagrange interpolation technique would find to be very useful, or technique which can be rightly applied. So this is a general approach. That perhaps is the reason you are taught, you are given the option of it. With this, I'm closing the lecture. As I said, we got about 10 minutes of discussion time. So queries may please be put forward. So I should be able to answer to you from the space in which we have discussed. Okay, madam.
Yes, sir. Hello, sir. Am I audible?
Yeah.
Sriji here. Sir,
Yes, Sriji.
that's sir. Many were asking about this real life applications of this formula, and I think you just pointed some of it, right, sir? So if you could add some more points or on sorry, sir.
Yeah, please go ahead. What are the specific requirement? Hello.
Sir, somewhere, I mean, many of them were asking about the real life applications of the formula. Yeah. And I think sir discussed just now one of those points. Sir, if anything more, I mean, could you add some more examples?
Yes, that's good. Yeah, I'll do that. As it's asked, where do you apply them? Because any engineering analysis, when you try to do, you don't get the total response of the system. You won't be able to, or we won't be able to provide the total data that is required to understand that. So if we need to identify, to get any data, well, let us say from this graph, from this particular, I'm just, if you put a slide 2, x1, y1, x2, y2, this slide is visible?
Yes, sir, it is visible.
Yeah. So this, if I'm trying to talk about this x1, y1, x2, y2, x3, y3, this data, wherever if you require any value in between, any data set, because whichever, maybe it can be in economics, it can be in your structural engineering, it can be in hydraulics, wherever if you need a data requirement in between, that can be used for interpolation. Perhaps the best example which I took out is on the problem. In that problem case, when we had discussed, I took about 5 data sets. We got about 5 data sets, and you will be asked to find most of the problems that comes up in that manner. You'll be asked to find the value of x equal to 4. Here I asked from a given set of data. So that's the data that we need to estimate. So our first objective is to get what is the general polynomial which you can use to represent the data. The polynomial will be a character of the data set. And once that polynomial you have got, in that polynomial you substitute the value x. So once that x value is given, you get what's the, so the polynomial will stand as what we call it as a general character of the total data set. When the data is given to you, you don't know, we are not in a position to understand what is the general character of the data, how they are connected. Now, interpolation will help us to connect this data point the best possible manner. So in between what is needed, they can give us. That's the main whole objective of interpolation. It has got wider application engineering, even as a mathematics, you will have different situations where interpolation needs to be practiced. A word of caution, if I say, what we need to understand is, let us say, if you try to interpolate, because we need to have to choose. Now the question that might come is, you have used linear interpolation, you have got quadratic interpolation. Now let us say, if you got interpolate collecting 5 data points, 8 data points, how can you choose that? That is there, it depends. You must have a prior information on characteristics of the data. Again, this I'll give a simple example again, same domain. The stress to strain plot which we have used. If you plot stress and if you plot strain, of course, all of us understand, they are in proportion. That's, is it elastic range? We call they remain in proportion. Stress is proportional to strain. That's why it's what we call as modulus elasticity. Now, one, they are in proportion, irrespective of any data point that is given elastic range, they are straight down. You don't have to go into a very complicated data polynomial to explain this, because they are going to be straight line. Any 2 data sets are going to be a straight line. So this we must be very careful, because when we try to apply very complex polynomial for a particular data, for example, here also, if you apply a quadratic polynomial here, when a quadratic polynomial is obtained, you get a quadratic function x squared, which will not satisfy this equation. Here it's a linear function, which is required because they are in proportion. This needs to be understood by the user of the equation. This is some guard which every user should. So whenever you apply a polynomial, we should be able to ask ourselves, in general case, not necessarily for an exam, not necessarily for exam, in a usual case, when you apply a polynomial equation, you should be able to understand what the general character of data, because you should not use a wrong polynomial for a wrong characteristic. As I told earlier, if your straight line is the general function, you fit it with a quadratic, your polynomial answer. This difference is that okay?
Yeah, okay, sir. And so we have one question from a student that how can we find f of 2.3 in this question? So he has asked that, and I think it's doubt from that solved problem.
Okay, great. Now, see, if a 2.3 is asked, let me take up this. Yeah. Yeah, 2.3. 2.3, let us say. 2 is your x naught.
Sir, sorry to intervene. Can you please make it to full screen?
Okay. Is that okay?
Yeah, okay, sir. Okay, sir. Okay.
Yeah. Now the question is, how can I get to 0.5? Your value here, this is general polynomial that you use. Now your x value is 2, x1 value is 3. Your 2.5 comes in between. So in this x value, instead of 4, it will go into 2.5 value. That's it. No other change. Because what we got from here is a general polynomial. And your input requirement, you require a value of 2.5 for x. So let's substitute the value x equals 2.5 in this polynomial and get the result. So maybe here, as you come here, your 2.5 x will take the values 2.5 here, 2.5, 2.5, 2.5. And instead of 4, you'll have to write f function giving the value 2.5. So you get the and value corresponding to 2.5. This is a very simple substitution that you need to do. Shriji, is that okay?
Yeah, okay, sir.
Yes,
sir. I think that a student will practice by substituting his values and he'll get the answer.
Good.
And sir, another student, she's asking from an exam point of view. She's asking, is this derivation important?
Okay, it's not. It's like this, exams as a teacher and use a set of students. Of course, it's a computational course, and you are expected to learn use this formula. So, anyway, general equation of polynomial you should try to keep in your mind because that is needed. Based on which you can tailor down to linear, quadratic, or required number. So that's maybe perhaps if you practice you'll be able to get that. Now on the derivation is not a very complicated. Perhaps when you write it down on paper, it's a very simple 2-3 steps alone. And in case if a small understanding level question is asked, prepare a short description on Lagrange Interpolation method. You should be in a position to answer that question in a better manner. So hence fetch the full credit. So under that scenario, it's just a half a page note. I would rather the student put some time to understand this and write. Because looking this as a numerical course and we just master ourselves to use the equation alone might be enough from an engineering perspective. That might be enough. But from an exam perspective, you should be able to address different ways in which university might test you. So I would rather request, the topic is a very simple derivation, it's not a very complex derivation. Perhaps it's better that they try to master this as to make them more confident to approach the exam. Shriji?
Okay, sir. Okay. Sir, so I think we have reached to the end of the session, and we have only 1 hour time. We had only 1 hour time, and sir, so I think we can just conclude the session. Thank you, sir. Thank you so much for your session, and we are so happy to associate with you. And I think it's a good opportunity for students who attended today's session. We had Professor Praveen here, who has an experience of over 20 years in this teaching field. So thank you once again, sir, for the session.
Thank you so much, Shriji. Of course, I think people are not clear.
Okay, sir. And to the attendees, I'd like to inform that we will be providing this session and all these slides in online, so you can again use this until these portions are thorough with you. So that's it, and I'm just concluding the session. So thank you all.